Hello and welcome to Econometrics with James Bland. Today we're going to be learning about the over-identification test. Okay, so just as a quick recap on what we were doing before, we were looking at estimating an instrumental variables model using two-stage least squares. So the model we had in directed acyclic graph format looked like this, right? We had an X that caused Y, and we wanted to estimate the causal effect of X on Y. The trouble was that there's an unobserved error term, a confounder here, that affects both X and Y, so OLS is going to be no good. So fortunately, what we have in our hypothetical data set at this point is an instrument that affects X, but does not, is not correlated with the error term. Okay, but the thing with this is that you might also have a second instrument. So this might be our Z1, and we have a second instrument over here. And so if we can if we can come up with a good story for why the exclusion condition holds for both of these, then we can include both of these in the first stage of our regression. Now, if you think about this, a result of this is that if both of the instruments are good, then beta 1 hat, if we use Z1, and beta 1 hat if we use Z2, and also beta 1 hat if we use Z1 and Z2, should all return roughly the same number, right? If we use one valid instrument, we should estimate the causal effect. Well, if we use another valid instrument, we should also unbiasedly estimate this causal effect. And if we use both valid instruments, then we should also unbiasedly estimate the causal effect. However, note that if one of these instruments is not so good, sorry, this should be our Z2, if one of these instruments is not so good, in the sense that maybe Z2 is correlated with the unobserved error term, or something like that, then we might get different estimates depending on which of these estimators we use. Okay, so you can go ahead and read some of the more technical details of the over-identification test, but basically what we're doing here is comparing beta 1 hat Z1 and beta 1 hat Z2. Okay, so let's have a think about our decision rule here. Okay, so if we're looking at beta 1 hat based on Z1 and Z2, if beta 1 hat Z1 is approximately equal to beta 1 hat Z2, then, loosely speaking, we could conclude that one of the following is true. So it could be that both Z1 and Z2 are valid instruments. Okay, but it could also be that both Z1 and Z2, excuse me, I will turn my sound off, are equally bad instruments. Okay, so if we get a result where beta 1 hat using Z1 and beta 1 hat using Z2 are close to each other, this is going to suggest that one of these two things are true, and we've got no way of working out which. Okay. If, on the other hand, anything else, which would be beta 1 hat Z1 is not approximately equal to beta 1 hat Z2, then at least one of Z1 and Z2 must be bad. Okay, as in not satisfying the exclusion condition. Okay, we don't know which one's which, but rejecting. So this is our null hypothesis, and this is our alternative. Okay, so this is qualitatively what our null and alternative hypotheses are, right? So if our null is true, then we're going to get something like this. If our alternative hypothesis is true, these being the nulls and the alternatives, then we'll get something like this. Okay, so I'm going to pick up where we left off, going through Scott Cunningham's fish market example, and use two of the instruments we have, and do this over-identification test. Okay, so here we are in Stata, and just as a reminder, I'm using Scott Cunningham's example from his online and soon-to-be-in-print textbook Causal Inference, the mixtape. If you want to use this dataset, you should go to his website and install the Ado file that's on this web page called SCUs, and that's going to allow you to run this command here, which just downloads the data from the internet for you. Once you're done with that, might also need to install SDout to produce the tables that I'm going to be showing you as well. Okay, don't think I'm going to do any plotting here, so let's get rid of this. So this is a cut down version of how I finished up with our previous example, and I'll post a link to that at the bottom of this video. Let's have a look at the data set we have here. So we're trying to estimate the own price elasticity of demand for fish using instrumental variables, and what I'm going to use here, we used, I think, wind speed in the previous example, and now we're going to use wave height. And so the working assumption here is that wind speed and wave height are things that affect fishing conditions, but they're not going to affect demand for fish. Okay, so those are the things we need to satisfy the exclusion condition, and now we're going to test whether these two instruments are valid, or at least either they're, well, if we fail to reject the null, then they're equally good or equally bad. Okay, so the to build up, what we're doing in the over-identification test, let's produce an STAB table that shows the three instrumental variables regressions that we could estimate using these two instruments, just with having log price and log quantity in the second stage. Okay, so we'd need to IV, let's do the one with both instruments first. IV regress, we're using two-stage least squares. The left-hand side variable is log quantity, and our right-hand side variable, which is endogenous, is log price. And now we're going to use speed 2 and wave 2 as our instruments. Okay, so if I run that, I get this. Let's maximize that window so you can see what's going on there, and then I will run it again. I have too many Stata windows open. Actually, I don't. Okay, so let's run this. And so we estimate this as a elasticity of 0.8, roughly. And so the question is, if we use one, or well, either one of these instruments, is our answer going to change here, right? Do we estimate a different elasticity if we use only one of these instruments? Okay, so let's go back to our do file. We're going to put this in a table because it's going to get hard to compare these to other things. So to do that, esto, this is going to be my column 1 of my table. And then I'm going to stab down here. I'm going to call everything column 1, 2, 3, and so on. So I'll use the wildcard here, so anything that starts with COL, just in case there's something else that's starting with COL, I'll put an underscore in there. I want to show standard errors, and I want to add some information here. So est add local speed yes, which means I'm using the wind speed variable. This is just adding some things here. I'm going to have height up here. And then down here, I'm going to tell the table to use this information. So these are called scalars. And I'm going to call them, I want to use speed and height. Okay. And I also want to use the variable labels. So let's see if that works. Yes, it does. Okay. So here's my the first column of my regression. I've got log price and log quantity. So here's my elasticity. This table is telling me I have 97 observations, and here are some here's some information about the instruments I'm using, and this is particularly interesting because, well, particularly useful because if I'm showing this in a seminar, maybe I don't want to show the first stage of the regression on the same slide. This way I can just, show the information I want people to see without cluttering up my slides and tables too much. Okay, and with that in mind, really all I care about is the coefficient on log price. So what I'm going to do here is keep just the coefficient on log price, which I have to capitalize correctly. And here we go, I've dropped the constant. Okay, so the keep command here tells me which variables are going to stay in the table. Okay, and I'm back with my second 15-minute budget of Screencast-O-Matic. Okay, so where we left off, we'd estimated this one instrumental variables model using both wind speed and wave height as our instruments for log price. Okay, but since we've got these instruments, there are a few other models that we could estimate, just thinking about the combinations that we could have. Okay, so I'm just going to copy and paste these in here so we can see them in the STAB table. Down we go. Here's our column 2. Let's just use wave height. Okay, so which means we're not using wave height in here. I'm just going to leave that blank. And then we'll make our column 3 over here where we just use wind speed. Okay, actually that's wave height there, and that is wind speed. So that's going to look like this. And now let's see what happens when that runs. Okay, now my STAB table has 3 columns, and note that a lot of things have changed. Well, maybe they haven't. So here, if I use just wave height, so that means I'm not using wind speed, getting an estimate of elasticity of about 0.85, whereas before it was 0.8. And then over here, I'm just using wind speed, which is getting me a negative but not significant estimate of elasticity. And so the question is, for the statistical test, are these numbers statistically different from each other? Okay, so if they're not statistically different from each other, then we would fail to reject our null, which would lead to our conclusion that either both instruments are good or both instruments are equally bad. Okay, and we can't tell the difference between those two. Okay, on the other hand, if we reject our null hypothesis, we can conclude that the instruments are differently bad, which, if you think about that, means that at least one of them is bad. Okay, so let's see if we can do the over-identification test, which we're going to do using this first, using this first column regression. So I'm going to go back to my code up here and run the over-identification command, which is stat overid. That's it. And I'm just going to put in a command here that Stata is not going to recognize, so we can stop the code at that point to look at the output. Okay, so here we are. If we go up a little bit, you can see the regression. It's the same one we saw in the column. Here's the new bit here. We've got the test for over-identification restrictions. It's given us 2 of them. Fortunately, we get the same conclusion. Okay. So here we have chi-squared 1. So if we think about this, we've got 2 instruments. We're testing to see whether the 2 instruments, well, using just one of the instruments, produces different results. And so those restricted models are going to have, you know, 1 instrument compared to the unrestricted model, which has 2. So we have 1 degree of freedom. You know, Stata's doing all of this for us. And so, you know, if you can't do chi-squared numbers in your head, which, you know, I don't think is reasonable anyway, you know, this is a pretty small number for a chi-squared 1, and so unsurprisingly the p-value is large. So here we'd fail to reject the null, which means that either both of our instruments are good or both of our instruments are equally bad. Okay, so we can't separate out those 2 conclusions, but we can conclude that well, either we're really good or we're really bad, and then you start to you might have a think about in your specific case what do you know about the instruments you're using. So for example, if you are really certain, or you have a really good story for why one of your instruments must be exogenous, right? It must satisfy the exclusion condition, then you can rule out part of the null hypothesis there. Okay, so one of the questions sometimes I give my econometrics students is sort of this hybrid experiment and instrumental variables problem where you know one of the instruments is exogenous. Okay, and so if you know that one of the instruments is exogenous and you fail to reject this test, then you can think about maybe ruling out the both instruments are equally bad because you know that one of them was deliberately randomized. Okay, you've also got to think about the size of this test. We're failing to reject the null, so what it's giving us here is, I mean this is the p-value, but if you think about that, you know, that we're doing a 5% test here, we're kind of, in this situation, this is kind of the opposite to how we're thinking about statistical significance if we're you know, hoping for a significant result, right? If we want our regression, and I'm not saying like we want anything as scientists, but you know, if we want our instruments to be good instruments, then we're hoping to fail to reject the null. Okay, so we're worried here about the power of the test. And if this is a very underpowered test, then we're going to fail to reject the null a lot, right? The test might not be very good at detecting instruments that are differently bad. Okay, so just remember that, you know, in a lot of the times when we're doing hypothesis testing, the interesting thing happens in terms of research, you know, recommendations that we can make from our research when we reject the null. personally integrate your loss function over your posterior estimate, but I teach frequentist econometrics, so here we are. The thing here is that we might be doing a reasonably underpowered test. Okay, so that's the over-identification test. That's a useful number that I might like to put into my STAB table. Okay, so after I run this over-identification test, I can type in return list, and it's giving me all of the things that Stata is storing after I run this over-identification test. Okay, and so what I'd like to do is to put one of these p-values into my STAB table to show my audience that, look, I did the over-identification test. It's not going to prove that my instruments are valid, but it's at least suggesting that they're not differently terrible. Okay, so I want to put this number into my STAB table, and me being the lazy person that I am, I don't want to copy and paste this every time I run a new specification, right? So I'm going to code this up so it appears in my STAB table, and so if I change any of my code, it's just going to update into my STAB table. Okay, so this is going to have another STAD local. Call it over ID, and that's going to be equal to this thing here, RP score. RP underscore score. Okay, and then I just have to tell it, STAB over here that I want to include the over-identification value in there. And it's not going to be populated for the others. It won't return an error. It just won't show it there, right? So we can't do an over-identification test for my columns 2 and 3 because I only have one instrument in those models, right? I can't test this against not using the instrument at all. Okay, so let's run this and see what we get. Okay, and well, let's put the number in there, but it's a pretty terrible level of rounding. I probably should round this off to 3 decimal places at most. So let's do that. I just want to, up here with my code, round that off to, let's see if that works, 3 decimal places. Nope, I think that's rounding it off to the nearest 3. This is what happens when you switch between R, MATLAB, and Stata. Let's try that one. Nice. Okay, so I've got the over-identification test, and p-value for that in there. Again, going through here, I might want to give these scalars more useful names in my table. So I can do it like this. Wind speed, height. Let's move this over here so you can see it a bit better. Wave height, over ID, call that over identification test p value. Okay, let's run that. And here now we have a little bit more information in our STAB table. Hooray! Now it's starting to get a bit hard to see here, and of course you probably don't want to copy and paste this into your Word document or even better, LaTeX document. So what you should be doing now is using maybe another line of STAB here. I like to have both here just so I can see the output, and I can also generate the output using fish, just give it a name, over id.rtf. So, most people, most of my students are using Word, sadly, so, change this to TEX if you want to have a LaTeX table. And then replace, so when the file exists, it's just going to overwrite it, gives Stata permission to overwrite the existing file. Run this, and it's generated the following table, which open up in Word. Have a look at that. Isn't that nice? Okay, so here you've got a reasonably journal quality table that you can copy and paste into whatever you like. If you're using LaTeX, again, just replace RTF with TEX, and it will give you a file that starts with begin tabular and it will finish with end tabular, and then you don't even have to copy and paste that into LaTeX. You can just use the input function in LaTeX to, you just give it the file path and it'll just put it in there for you. Okay, so I think I'll leave it at that. I'll have a think about some other things that I'd like to teach you about two-stage least squares and coding in Stata. But thank you very much. I'm James Bland. Have a good one.